Alright, we're now going to look at a trickier example where you have large number coefficients and you also have variables on both of the terms, and this is going to affect how you can actually factor this. So the general case is still going to be true. A plus b times a minus b is going to be a squared minus b squared. So this is going to be our a squared term. This will be the b squared term. That portion is the same. It's just for this example, we don't have perfect squares. So here's the catch here. We have two terms only in this expression, which means that should be a hint to you that you're either going to need to do like common factoring or a difference of squares. So those are the kind of two possibilities that we can get from just a two-term expression, and in some cases it's both. So earlier in the course we wouldn't have continued on to doing the perfect squares, but we are here now. So we first have to take out a greatest common factor of both of those numbers to see if we can get to a perfect square in each. So in terms of how you can actually get the greatest common factor of 98 and then 450, I will remind you that we have seen before prime factorization where we had the factor trees. So if you say, let's take the number 98, it's an even number, so I would always like to take 2 out as a factor. So 98 is like saying that's two groups of 49, and then 49 is 7 times 7, and then those are all of the prime factors of 98. So 2 times 7 times 7 is 98. For the number 450, again, it's an even number, so I would prefer to always take 2 out as a factor first. And then let's see, 450, that's two groups of 225. 225 is actually a perfect square, right? It's 15 times 15. And then each group of 15 is 3 by 5. So then the prime factorization of 450 would be 2 times 3 times 3 times 5 times 5. And then remembering common factor, it's just whatever the greatest common factor is based on whatever of these numbers that we're multiplying are common to both expressions here. So we have seen this quite a bit before. This is just a reminder. 2 is the only thing that's common. So the greatest common factor is 2. You might have been able to do that just by inspection, and I would not require you to actually do the factor trees to figure out a greatest common factor. It's just if it didn't automatically come to you and you immediately saw that pattern in the numbers, like it wasn't just automatic, and you're looking for some steps to follow to figure it out, this is what you would do. So now we know the greatest common factor is 2. Once we're at this point, now we're going to factor the number 2 out of that expression. So this will be 2, and then remembering, we've done common factoring quite a bit. So when you do common factoring, you take the original terms from the expression and then you divide them by the greatest common factor that you found. So 98x squared divided by 2 is going to be 49x squared. And then 450y squared divided by 2 is going to be 225y squared. And now what you should notice once we're at this step is that these 49x and 225y squared, those are both perfect squares. 7 squared is 49, and then 15 squared is 225. So now that we've handled the one greatest common factor and factored that out, now we have an expression in the brackets that does meet the requirements of difference of squares and does follow that general pattern up there. So at this point, Now we can start following the same procedure that we would have used in the previous examples. So if we want to know a, so this is our a squared term, we need to do the square root of that. So the square root of 49x squared is going to be equal to square root of 49 times the square root of x squared, which is going to be 7 times x. So 7x is going to be the a term. And then over here we will do the b term. So that will be the square root of 225y squared. So that's the square root of the number part and the square root of the variable part. The square root of 225, and you could use your calculator for this too, that's going to be 15. And then the square root of y squared is just y, so 15y is the b term. So notice that in this set of brackets we had the a squared minus the b squared. You didn't need to actually be concerned at all about which was positive and which was negative, because it just follows this general pattern that we kind of have to commit to memory, right? A squared minus b squared. This is just the a squared term. This is just the b squared term. When it comes to difference of squares, having a subtraction sign in front of the second term does not necessarily mean that this overall term is negative when it comes to factoring the difference of squares, right? Because we're not really doing algebra here, we're doing factoring. It's a different thing. But now that we have the a and the b term, we're just going to take this expression, make it fit that pattern. We cannot get rid of the 2 for the greatest common factor, so that should not disappear when you write the next line. We have to keep the greatest common factor in the expression, otherwise it's not equal. So the a term was 7x, so a plus b, the b term was 15y, so 7x plus 15y, and then that was multiplied by a minus b, so 7x minus 15y, and then that would be our final answer. 2 times 7x plus 15y times 7x minus 15y. And then if you ever wanted to check your work, you could simply expand out the binomials and then multiply that by the greatest common factor, and you should arrive at this same answer. And then that would be your way to prove to yourself that you had factored this correctly.